First up, it's really hot, and thanks a lot for coming over here and deciding to spend 2 hours in this session. I'll try my best to make sure each one of you gets satisfied with the whole training, and by the end of it, everybody understands a bit of what big data is. Yeah, in 2 hours we really cannot cover the whole topic, but let's make sure that we kind of globally understand what big data is overall, what Hadoop does for us, and stuff like that. Anytime you guys have questions, you can interrupt me and ask questions. The presentations is slightly big when you look at the questions that come in. We may not be able to complete everything in one session. If that's the case, we'll have another session in coming weeks. So but yeah, don't stop on your questions. Feel free to ask questions because I think that's important. All right. So let's get started. So we'll start with a small introduction. Is this clear? Can we switch off the lights? I think that will be, this will really, it's all white background. If you could just switch off the lights. Yeah. Yeah. Can you switch off a few there? Yeah. There? Yeah. Okay. So yeah, everybody should feel we are in a movie. That's fine. I think this, okay, you want to switch that off? It's okay. Clear? Clear now? Yeah, it will zoom in. It's a storytelling thing, so it will zoom in when it comes. So right now, I think the only thing you should be able to see is introduction. Okay. And anybody who's able to see what's inside also, then you really have very good eyes. So yeah. So then we'll talk about what is big data. We'll talk about what is Hadoop. We'll talk about a few projects that have originated from Hadoop and have become kind of individual products. We call them as Hadoop ecosystem. And we'll talk about where exactly Hadoop fits in the real world. Along with that, we'll take all your questions. So, as and when questions come, feel free to interrupt me. So, let's talk about what we are going to cover in this session. And if at all, we run out of time, next session will be there, continuation of it will be there. So, the first goal of the session would be to introduce you what is big data. Then we'll talk about what is Hadoop. We'll talk about how Hadoop works. We'll get friendly with stuff like HDFS and MapReduce. I hope everybody's heard of them vaguely. Get aware of Hadoop ecosystem, the projects that are around Hadoop, and understand how exactly Hadoop fits in the real world. A small advertisement of myself. My name is Ravi, around 7+ years of IT experience. Worked with companies like TCS and have served companies like Yahoo for Hadoop projects. And that's about it. So let's get started. Now, before we really talk about what is big data, what is Hadoop and all that stuff, let's talk about why exactly are we here on a Saturday afternoon when we could have really had a good rest. Why big data is really so important. Why there is so much buzz around big data. As per IDC, it's Internet Data Corporation, that's the agency which basically collects all the data about internet and all the market research that they do. They say that in few years from now, big data will be a $24 billion market. In next 3 years, you would have another 45 lakh jobs created only on big data. And as of today, as of this moment, in United States alone, there are 2 lakh less, or there's a shortage of 2 lakh big data professionals as of today. So we are not talking about couple of years from now. We are talking about as of now. There are 2 lakh, people who are required who should know big data, but there aren't enough people. So be it an individual person who really wants to, look for a better career maybe, or somebody who's come from a startup and let's say he wants to explore to grow in certain way in some other area. Big data is a space where there is a lot of growth. There is a lot of growth for, let's say, people who are fresh. There is a lot of growth for people who are, veteran in their own field and now want to look for something interesting. And there is a lot of growth for companies as such to look for better projects and, more innovative, more niche So basically have better, bottom line or profit, whatever you call it. So big data is real. It's no more a buzzword. People are using it to their advantage, and it's time for us to really, basically understand that and see if we can capitalize on it. I think end of the day, that's the goal. Now let's talk about what is big data. In the simplest of terms, really they say that either, layman terms, or in your, we say that in our grandmother's language, big data is any data that one machine cannot handle in terms of storage or processing. The simplest definition. If you have all the money on earth, you can still buy one physical machine that can have the max of 64 gigabytes of RAM and maybe 64 terabytes of data. One single machine, you simply cannot buy a bigger machine than that. But take example of Facebook. Per day they generate 100 terabytes of data, right? So the best money can buy is 64 terabytes, but in a day Facebook generates hundreds of terabytes of data. Take photographs, take likes, take comments. Imagine the massive data that gets generated. So any data that typically one machine would not be able to handle is typically termed as big data. Now there are few more characteristics to it, but at the raw form, this is the simplest definition. Now, if you go by definition, big data is amount of data that is beyond the storage and processing capabilities of a single physical machine. Clear? Now, data that has extra large volume and it comes from variety of sources. So there are two more characteristics to the data. So data that's really huge comes from variety of sources. So far we've been in IT and we are really used to play with databases. Everything is structured, everything is transactional in nature. But in big data, what people really talk about is data that is slightly unstructured. Can be your Facebook post, can be your Twitter post, can be the data that is there in your weblogs. Okay? So data that has huge volume comes from variety of sources in variety of formats and comes to you at a great speed. That's velocity. Imagine in a day how much data that is getting generated to, let's say, Facebook or Amazon. Let's say Amazon records all your browsing history. How much data would they be generating in a day? Few terabytes. So any data, when people talk about, okay, what is big data? It's data that's really huge, comes from variety of sources, variety of formats, and comes to you at a great speed. It'll get clear as we go ahead. We'll look at some examples, and then it gets clear as to what exactly big data is all about. So far, any questions? Awesome. So as I said, there are three characteristics of big data. First, volume, really huge volume. Second, variety, comes from variety of sources and in variety of formats. Third, velocity, comes to you at a great speed. So the data that gets generating, it's really fast. In a very, very crude way, if you want to really visualize big data, this is a very crude diagram, but just to convey the point. Let's say you have the best money can buy, single physical box, but the data is more than that machine. One machine is not able to handle it. That's volume. Data comes to you at tremendous speed. So the data that is getting generated every minute is really huge. That's velocity. And data can come from anywhere, not just your Oracle database, but it can come from your weblogs, can come from your tweets, can come from your Facebook posts. Okay, can come in XML formats, can come in JSON formats, can be any format. Now, this in a very crude way is what big data is all about. Big data is a lot of data in any form that is not just structural and comes to you at a great speed. Now, have been taking a lot of workshops, and a lot of times the students would come over and ask a few questions, typically very normal questions on what is big data and all that stuff. So while compiling them, I thought it would be good to put those logical questions in a slide and tell you what typically people ask and what are the answers to those questions, and then we go to the next topic. Now a lot of people ask, we understand what is big data, it's fine, it's clear. But how does it look like? When somebody tells me what is big data, how do I visualize it? Okay. So there's no defined set of what is big data, what is not. Big data can be any data that is not really following a great structure, can be your RFID system generated files, can be your web logs, can be your user interaction logs, can be your transaction history, can be tweets, and can be climate sensor data. Now take example. If you are interested with a task of telling that how has Pune's weather behaved in past 20 years, how much data will that be? If you wanted to really come up with a pattern that in past 20 years, overall the Pune's weather, let's say you want to just arrive at a small conclusion that how Pune has changed in terms of weather in 20 years. How much data will you be analyzing? And will that data be stored in a database somewhere? Is it possible? Will Oracle be enough to store that much data? We agree that yeah, it will not be stored in Oracle, or you feel Oracle will be enough? Okay, tell me. It won't be sufficient. So while databases are really good, they have limitations. You cannot store infinite data, right? So if you wanted to really do analysis of 20 years of Pune's data, you simply cannot use Oracle database and do analysis. You will have to find some other way to do it. And it can, the data that is stored will always be typically log files, will not be really, all the database queries won't be running on top of it. Is it making sense? What do we do with this data? It's fine. A lot of data is getting generated. Amazon is having a lot of data. Facebook is having a lot of data. Today your company will have a lot of data. Tomorrow my company will have a lot of data. What do you do with this data? Okay. One thing, this is not transactional data. Okay. Transactional data is typically stored in a database. What do you do with this data? You analyze it. What's the value of taking so much pain in analyzing this data? It's fine. There's a lot of data. I agree. It's not in my database. It's in log files. But I feel it's useless. Why should I care about analyzing that? There is a lot of value to that data. Let's talk about it. How many of you have vaguely visited Amazon or shopped on Amazon? Raise your hands. Wow. So have you seen this, that if you look for an Xbox game and let's say you purchase or you browse couple of games, Amazon starts recommending you the games now. Everybody seen it? So imagine this, that every user who's performing the action, Amazon is learning out of it and recommending new things, right? Now a database cannot store all this data. Every click that you do, database cannot store. So Amazon is storing it in certain log files in some way. But what they are really doing is they are analyzing all. And when you go, they realize, okay, this guy, you know what, he's typically interested in games. So I'll give him a deal on games. Now because Amazon understands your behavior, the probability of you buying the game increases. We all agree? I'll give you a fantastic example of a friend who was explaining this. He recently had a baby boy. And he uploaded photos on Facebook. After a couple of days, he started seeing ads on the right which were related to baby products. One of the ad read that we are a company called Engrave and we take photographs and we pierce them on a wooden frame. Okay. He instantly clicked, he went, he made a purchase of 3,200 rupees. So this is the value of that data. Now Facebook cannot really store all your clicks in a typical database where they really store it in log files in some structure. But what they really do is they analyze. Once they analyze, they understand you better. Once they analyze and understand you better, they can better position you the products. And the probability of you buying will increase. Are you able to relate the whole picture? If there was a site that was just dumb, which was taking your log files but doing nothing with it, you will always get similar behavior. But if the site was trying to figure out who are you, what is going with you, and start positioning those products around you, the probability of you purchasing really go high. Agree? Now, this is where, this is what we are really talking about when we say that analyzing this data. Till yesterday, this was considered to be a useless data. Nobody bothered. Uh, how many of you guys, how many of you have worked on web applications? Wow, fantastic. How many of you have come across a scenario where probably your boss would say, fine, we have a database where transactions are stored, but analyze your log files to figure out who the user is. How many of you really come across that scenario? So basically data was there. Have we ever taken the pain to analyze it? It may give us some information that would be fantastic, right? But so far, no small businesses really were able to do it. Why? Because maybe it was very painful to analyze the data which is in unstructured format. Is it making sense so far? Any questions? All clear? So the idea is, this data isn't really critical for your business, but if you analyze it, you can really make a lot of money. Facebook is doing it, Amazon is doing it. That's how, this whole industry is working. Till yesterday, this was limited to all big guys, but today in public domain also there is a lot of data. If you start a company tomorrow, who knows, within a week or 2 weeks or 2 months or 3 months, you may be dealing with a terabyte of data. So now even you need to start analyzing how should I capitalize on this data. So that's where big data is for everyone. Now, let's talk about a few use cases what people have done with big data. How many of you heard of Rackspace? Okay. Rackspace, there's a very famous case study with Rackspace that they wanted to analyze, we want to bring down our system for 20 minutes for maintenance in each country. What time should we bring down in every country? How do you decide that? Fantastic. How do you really come to that conclusion? Huh? What? Correct. But if you were to go for analyzing email logs of like server logs of email service, how much logs will that be? Let's say their email service is running in 200 countries. Analyzing all the logs to just figure out when should I bring down my service in India. So let's say, you have to come to an answer where Indian people, they use Rackspace email service minimum at Sunday morning, 3 to 3:20. We can bring down system at 3 to 3:20. To really arrive to this decision, how much data will you be analyzing? Yeah. So, these are few use cases, but people have done that. So when Rackspace has done that, they have more accurate information. Typically, how we would take decision, very gut feeling whether, just bring down at this time. But here they had facts. So similarly, if you are analyzing this data, you are always at a benefit. So these are few use cases. Identifying the customers who are most important to you. Identifying the best time to perform maintenance based on the usage patterns. Okay. Analyzing your brand's reputation by analyzing social media. This is another use case of big data where people are analyzing a lot of data to come with something very important. Let's say HDFC Bank, take example. They want to figure out what people are really talking about my bank. In a day, there are millions of transactions happening on HDFC. There would be few people who are very happy about them. There are few people who are frustrated about them, right? And people have wrote about them all over the web. If they don't listen to the customer, someday customer will easily go to some other bank, correct? So then they use, technologies around big data basically, or any company would use to basically aggregate this data and see what people are talking about me. Take example, you as a frustrated user went on Facebook page and wrote, HDFC customer service sucks. Okay. Now when HDFC realizes that, they get back to you with an email that we were sorry with this, we'll fix this problem for you. And they have this customer for lifetime then, right? So this is how a lot of businesses are using technologies around big data. We will get to what exactly technologies are, but for now we are trying to analyze what is big data and why it is so important. How can such huge data be analyzed? Now, just in a simple way, just answer this question in a very straightforward way. Let's say, in a very layman terms, if one machine is not able to do my job, what will I do? Huh? But how do you split it? Fantastic. So we need to find some way, some magic to do distribution. One machine is not able to do my job. Some way to do distribution. Agree? We all agree to this? So far, any questions on this? So it's important that you visualize. So you know, technology is another part which is very easy to do. The real part is to visualize why are we doing something. So we realize that yeah, data is really huge. One machine is not able to do. We need some way of distribution, some magical way. Agree? So we are talking about distributed computing. Agree? But the question comes, once you see this now, as the volume is beyond processing and the storage ability of a single physical machine, some distributed way has to be used. We all agree universally? All agreed? The next point that comes is, wait, distributed systems like MPI have been around for more than a decade. Since our college days, we all had subject on distributed computing, right? Everyone? So the question is, distributed systems like MPI have been around for more than a decade. So do we even need to take this course further? Does world really need one more distributed system? Do we really need to spoil our Saturday and come over here and talk about distributed computing, which is already there for so long? Everybody's heard of distributed computing, right? Some magical way to distribute your load, your storage and all that stuff. That is already there. So does the world really need one more distributed computing framework? And what's such a big deal about it? So what we believe, or what world believed, was we really need one more distributed computing framework. So the answer is yes. Now let's talk about why do we need another distributed computing framework. So far, any questions on this? Is it making sense? Yeah, go ahead.
When did people start taking office of big data?
When?
When did people start taking office of big data? People were not aware that the data is huge and it is important. When did they realize the importance?
See, the idea is, a few years before, there was not much data available to, let's say, small startups, or so there were few big companies, Yahoo, up to some extent Amazon, and let's say companies like Google. Only they were really fighting the challenge of data. We small players never had any problem with the data, right? How much data did you have access to, let's say, a couple of years back? But as the data increased, people wanted to find ways to do things. And that's when, people have started waking up to this, that, okay, my data is increasing right now, I need to find a way to do something. So Hadoop, or whatever big data technology we are talking about, it's been around for 3 to 4 years now. But as of now, people are waking up because even a small startup may have a lot of data. Take example, you start a new photo tagging service, okay? So basically, people upload photo on your website. You are a startup, you are just 5 guys in a company, okay? People will upload photos on your website through mobile or on PC, and you will just let them tag. Within a month, how much data you may be dealing with if your service really goes a big hit? A lot of data, right? So 4 years before, big data was a problem for Amazon, Facebook, Yahoo. Today it's a problem for everyone. 2 reasons. 4 years before, nobody thought that they will play with so much data. Second, these companies have told people how they are smartly using the data. So even banks had a lot of data, but they never figured out how to really use it. When they looked at what Facebook and all are doing, they felt even we could do something about it. Take a small example of fraud detection. 10 years before you did a fraud with some bank in Mumbai, or let's say in Delhi, you are in Pune. What is the probability that today they will find it, something that happened 10 years before? What is the probability? It may be possible, but what is the probability? Very less probability. Today it's possible. With systems like these, it's possible. And a lot of banks are working towards this. So data was always there. Banks never realized that they can put this data around and play with it. Maybe there were technologies that were not easily available, and it were only available to Facebook, Amazon and stuff. Today it is wide open. Correct.
That was also one of the reasons why big data came into picture for the big players, because they had the resources and the vision to go behind the market as well.
Exactly. So that's precisely the point, that few big players had resources, had technologies with them, where they were able to play with this data and do something meaningful. That's precisely the point, and that's what Amazon did. But technologies that were there involved a lot of investment, so no small player can go behind them. Today it's possible. That's the whole point. So yeah, perfectly added. Any other questions? Yeah. Not log files only, any data for that matter. Yeah, it can be database also. Exactly. So see, we are not, log files is just an example of it. Data can be any format. Take example, Twitter may give you your output in JSON format. JSON is normally, it's necessarily not a log file. It's a file format, but you can very well, put that in and do your analysis on top of it. So the idea is, the format is the whole system or the technologies around it are format agnostic. So we cannot say only this data will be analyzed. Any data can be analyzed. You should be capable to write a program around that. So logs was one of the example, because we all are so programmed to think data in terms of database, that the other format that we really know is logs only. Even JSON, a lot of companies are using JSON now. Even XML data can be huge data at times. The system will let you do anything you want. We'll talk about the system later on. Yeah. Go ahead. Not 100%, but very close to it, yes. But eventually they'll not replace, because the point is this. Databases are a different use case, or data warehouses. Databases are perfect for querying data. Okay. These technologies are more towards, writing programs and analyzing them. They are not really real time. Any technology we are talking about, big data, is not a real time technology. Data will come in and you will play with it. Okay. So data warehousing tools will still stay. They will play nicely with big data, but they are not going to, big data is not going to replace them anywhere. Yeah. And a lot of people feel that, yeah, this is going to be a solution to the entire problem. That's not the case. It fits into certain cases, and whether a tool has to be used or not, it depends on entirely on your project. Okay. So that you as an architect have to be smart enough. So at your home, you will have a hammer, and you will have some other tool. Whether you have to use hammer or not, hammer is there, but whether you want to use it or not, as an architect, you will always have to choose that. Okay. We can talk about a few real world this thing. I have a last slide which will talk about where it fits typically, but whether to use it or not, entirely, it seriously depends on whether it fits or not. Take example, one of my student asked, I have 100 terabytes of data, but data is not getting generated every now and then. I have it, I want to analyze it, but new data is not getting generated. Should I go for Hadoop? Now, the answer can be both yes or no. If you really know the future, will that data be coming again? Then you say, you should invest in it. If not, don't distribute it. Keep it separate, just do your job. And so, all I'm trying to really say is that it is not like one size fits all. This is a technology. You have to take a very neutral approach that, okay, this is it for me to use, but you have to figure out, should I use it or not? Making sense? So don't, just because you have money and you want to take loads of goods from one place to another, don't buy Mercedes. A Tata van will do for you, right? I mean, something that takes a load for you. You're getting the point. So have that use cases clearly in your mind. So we were talking about, yeah, go ahead. Yes. Correct, correct. Okay, I'll put it this way. Now, whether you want to show something that's common or something personal to the user, it's always the question of the business guy who's writing the specs of the product. Okay, both the facilities are available. What you are talking about YouTube, where the recommendations are based on the video and not on you. We all agree? That discipline of machine learning is called as collaborative filtering. Okay, it's a slightly complex thing, but I'll tell you. Collaborative filtering means every time somebody does something, the system takes input from everyone and says, okay, anybody who saw India's World Cup winning video will be interested in India's 1996 India-Pakistan match. How does the system learn? Their user isn't a component. Everybody is a component. That's called as collaborative filtering. Second is personalization, where you on Amazon went and saw Xbox games. So definitely you're not going to get another recommendation for baby nappies. But if you had a baby, you bought nappies, you would see another toy for baby as a recommendation. That's personalization. Now, whether to use personalization or collaborativeness is something the product manager decides. Technologies are available for both. How many of you have seen this in Amazon, that when you visit a particular product page, you see bottom, people who bought this also bought this. Yeah, that is collaborative filtering. Why? Because that time they don't care who you are. They just say anybody who bought a pen did also buy a pencil. And you as a component have nothing to do with it. But when you visit their homepage next time, they say you recommendations for you. And because you were buying Xbox games, now you see all the Xbox games. So the first thing on the homepage, what happens is called as personalization, really attacking you. And what you saw that people who bought pen also bought pencil is called as collaborative filtering. So that topic of machine learning subject is called as collaborative filtering. You take input from everyone and try to come up with some decisions. That, you know, typically people who prefer India's World Cup video will also see India's India-Pakistan video. Yeah, go ahead.
I got an email from email saying the subject was skydiving photos.
Huh?
Skydiving photos.
Correct.
And then immediately I got an ad saying bungee jumping institute or something.
Correct.
Is that collaborative filtering or personalization?
This is personalization. The reason is this. This is personalization, but of a slightly different way. What Google does is when you get your email, Google scans what that email is for keywords and then puts the stuff. But is it hardcore personalization? No. It is more like there is an email and based on that, it is showing. So, but we cannot say that it's collaborative filtering. It is a mix of both, because the email gets delivered straight into your inbox. The keywords, and then you get the ads. Correct. Yeah, so again, as I said, that see, technologies are available and it's the product manager and the product group decides what you want to show before. Take example, when you search on Google, on your browser, if you see when you search on top, there is a search bar, right? Google will first show you what you've searched previously. So you start typing, the first suggestion would be the one you've used. Now, there are technologies available, as I said. It's the product management team that decides what experience you want to give to the user.
March 2012, Google had got a new user privacy agreement. It said that henceforth they are going to use all the data from all your accounts related to Google and merge it and show you. That might be the reason why it is so personalized when you use Google Chrome, because Chrome is from Google, Google is from Google, Gmail is from Google, and this happened in March 2012.
Yeah, so as I said, see, the idea here is that there is certain exposure that you have and the group or the company decides how you want to play with the data. So let's say as per this March 2012 agreement, they decided that they have certain data of you, how are they going to play with it? Technologies are available, they just play with it. Exactly. So for few people it is good, for few people it is not good. If I have uploaded my baby's photo and then I see ads of my baby, then I mean related to that I kind of get irritated maybe. That somebody is tracking me to this level that they know what is happening in my personal life. I might not want, you know, somebody to poke that and tell me. So there are both schools of thoughts. So I'm not getting into what is right, what is wrong. The product is there and people decide how they want to play with it. The whole point is that. Yeah. Yeah, the last slide will be having that. Yeah. Last slide will be talking about that. We'll talk about the use cases. Clear? We go ahead. So we were talking about distributed computing being around. We've been all we've heard of something like MPI or Corba in our schools, colleges, and why are we really talking about this thing here? So the world really needs another distributed computing, and this is why. A typical distributed computing system on a very high level, okay, I'm not getting into the specifics of it, works like this. You have a storage area network. Internally there are disks, but this storage area network is like one infinite storage that can store all the data. How many have heard of SAN? So SAN is a big storage which has all the data inside it. You have your application servers. So you have server 1, server 2, server 3. On each server you will put your Java program, and each Java program will read the data, take it here and process it. Each Java program completes its own task, and then you finally get the output. Agree? Typically this is how distributed computing has been around. So let's look at the flow. Programs run on each app server. All the data is in storage area network. Before execution, each server gets data from SAN. After execution, each server writes output to the SAN. Clear? This is how distributed computing has been around. This approach had certain problems. Before we go to the next slide, can somebody tell a few problems that you guys see in this? Yeah? Fantastic. Fantastic. Any other? Pretty same, yeah. Good. Any other issues that you see with this? Partly, but a storage network, there is nothing that it's, yeah, the probability of a storage going down is slightly less because it's just a dumb piece of storage which is not doing anything that, you know, may crash. But let's say we take that point also. Huh? Fantastic. You are like almost there, yeah. Part of it, part of it. Yeah, there is one point which will talk about that. Yeah. Brilliant, brilliant. So let's talk about that in the next slide, and we'll relate to all the points. Problems with that system. Huge dependency on network, huge bandwidth. Why? Because if I have 10 terabytes of data, each Java program reading 1 terabyte of data each, assuming every Java program reading 1 terabyte, processing it, writing the output back. So the whole network gets choked up completely. So there is a huge, huge, huge dependency on the network and the bandwidth. Scaling up and scaling down is not a smooth process. Pretty much what, you know, this point was, when you first write a program, you will have to take consideration of how many nodes are you going to run the program on, some part of it. So I cannot just take first 10 nodes and then increase to 1000 nodes and your program will run. That's not going to be the case. So at the same time, if I am running 100 nodes, what if 77th node fails? It's not that it's not recoverable, but you as a programmer had to take the responsibility of it. It is a very big pain because if your boss says, or if your manager says, well, we have 10 million rows of records, you have to sort it. You better write logic which will sort the data, right? You don't want to write logic of what if 77 node fails, how will I recover that? what as a programmer you want to focus? You want to focus on the business logic. What your manager said, I want to sort the data. Do you really want to spend time on what if 73rd node fails? But in this case, you will have to take that pain, unfortunately. Agree? Partial failures are difficult to handle. So it's the same point. Scaling up and scaling down is tough. I cannot add nodes and remove nodes when the program is running. Partial failures are very, very difficult to handle, and the developer had to take the pain of it. A lot of processing power was spent on transporting data. If you see, if there's a distributed computing framework, system that we are talking about, you'll be spending 80% of your energy really transporting data and 20% of energy just running your programs. I mean, such a wastage. Data synchronization is required during exchange. So basically what this point talks about is, now 100 nodes are running, they are dealing with this much of data, but you as a programmer had the responsibility to combine that output. That was one problem. Second thing, all the nodes in the system had the responsibility to know what others are doing, because they don't want to end up operating on the same data that somebody else is working on. Agree? So these were real problems in a typical distributed framework. So we all agree that world really needed something else, not this, because if this was the case, basically your business logic will take 20% of your energy and 80% you're just doing something that is not your business logic. I mean, we all really want to focus on business logic, right? So that's why distributed computing never became really famous. How many companies do you really find that people use distributed computing? Has it really become a common buzzword? It's been around for 15 years. How many people you find working on them? It has really never caught up. And that's why world needed a better way to do things, and that's when Hadoop comes in. This is where, so it's like whole world is in trouble and Spider-Man comes to save everybody. That's how, Hadoop comes in. All right. So far what we've discussed is, let's go logically. We talk about what is big data. We talk about what you can do with it. You talk about distributed computing, which was there, and then you talk about the problems with it. So far what we've covered is typical distributed system. We covered what is big data. We've covered why does it need your attention. Any questions on big data so far? So far we have not spoke about anything about Hadoop or something. Let's first talk about the problem. Solution will come later on, that's fine. Any questions on big data? Everyone is clear? Awesome. So we go to the next topic, that is, what is Hadoop? So we all agree Hadoop is some magical way of doing distributed computing, a better way of doing it. Let's look at few book definitions. Let's talk about few bookish things, and then we can, get deeper into it. Anytime it's a break time, just let me know. I'm another 15 minutes, right? Okay. So Apache Hadoop software library is a framework that allows for the distributed processing of large data sets across clusters of computer using simple programming models. So basically, for now, it's some magical way of storing a lot of data. So it's some magical way of making sure that few machines work together. They store your data and you process it also. Clear? So as of now, what we have covered, some magical way, few machines will work together. I don't know how, you don't worry about how. You will store your data all together and you will be able to process your data and get the output that you want. In more simplistic terms, Hadoop is a framework that facilitates functioning of several machines together to achieve the goal of analyzing large sets of data. Now, there is an interesting history to it. The first company on earth that really felt that they were really they were having a lot of data was actually Google. Google felt that they simply cannot handle the data. So they created a distributed computing framework. They ran it for a couple of years, they liked it, and then they published white papers. They did not open source it. They just published white papers to the community saying that This is how we manage our big data. So one smart guy called Doug Cutting, he read those white papers, and he felt, can we develop something like this for open source? So he started working on a project called Hadoop. So while he was working, Yahoo felt the idea was really interesting, because even Yahoo was feeling, how do I manage so much data? And Yahoo recruited him. And they developed a team where they made Hadoop. Yahoo ran it for a couple of years, and then Yahoo made it open source for everyone. So if Hadoop is common today, it's fairly cheap to deploy and all that stuff. A big thanks should go to Yahoo, because they have developed this whole thing along with Doug Cutting, and they open sourced it to the community. So Yahoo is what has decided to basically give this whole project Hadoop to the open source community, to Apache. So Google created its own distributed computing framework and published papers about the same. Hadoop was developed on basis of those papers released by Google. Now, when we were talking about some distributed way of doing things, when we say distributed computing, we need two things: ability to store a lot of data and ability to process. Agree? Clear? Why do we need ability to process the data? Huh? Fantastic. Good. So everybody is awake. So Hadoop consists of two core components: the storage part. The storage part is called as HDFS, okay, and the processing part is called as MapReduce. That's the processing part. It will get clear as we come. We may, play a small game around it. Who knows? Yeah. Let's see if time permits. A set of machines running HDFS and MapReduce is known as a Hadoop cluster. I'm sure everybody would have heard what people talking about Hadoop cluster and all that. So a Hadoop cluster means a set of machines that run HDFS and MapReduce, storage and processing. An individual machine is called as node, and a cluster can have anywhere between 1 node to 1,000 nodes. Can be anything. The biggest cluster that typically people are running is in Cloudera, which is 4,000 node cluster. So 4,000 machines are working together to provide you storage and processing. And this is the simplest way you can visualize Hadoop. Very simple way. You see certain machines together. They are working as if they are one machine. There's like data gets in, and they provide you processing and storage. They provide you some magical way of storing all the data and process it. Clear? Now let's go deep. So all that was fine. So we were traveling in a helicopter like 30,000 feet above, and we were seeing world was really interesting. Now get to the ground and understand the depth of it. Let's visualize what is Hadoop. Hadoop has a master node, and it has a lot of slave nodes. In typical configuration, there is one master node, and there can be thousands of slave nodes. To easily visualize it, one manager and its team. Okay. On the master node, there are two guys who are masters. The master for storage is called as HDFS, Hadoop Distributed File System, and the node, the process name is called as name node. It's called name node. And the guy who takes off processing is called as MapReduce or job tracker. So the Java process is called as job tracker. On the slave nodes, you have storage and processing. The storage guy is called as data node, and the processing guy is called as task tracker. So this is how, on a very high level, Hadoop looks like. So you'll have like 7 people say there is a 5 node cluster. There is one master. There are 4 slaves. On the master, you'll have name node and job tracker running, and on the slave nodes, you'll have data node and task tracker running. That's Hadoop for you. Now let's look at this, and then we may play a small exercise, and then we can probably break for 5-10 minutes. So what happens is, let's say this is your Hadoop cluster. Assuming that we all work together, I am the guy who's setting up cluster for you. You guys have your laptops. The cluster is set up in your data center. From your laptop, what you will do is, you will tell the Hadoop cluster, this is my program and this is my data. So first, data will get transported inside, then you transport the program, and the program starts running on the data. First thing to remember is, to play with your data, wherever it is, it has to first go inside the cluster. Without that, you cannot process your data. Very important point. Without your data getting inside this cluster, you will not be able to process it. So step one is, the data has to reach, only then your program can start. Is this clear? So, step one, you have client who's first telling where my data is and how it has to be transported. The data gets in. First, the data gets in some magical way. Don't worry about it. We'll talk about it. After that is done, you package your code in a jar file. Typically, jar file is the standard. So you put all your Java code there, package a jar, give it to the cluster from your laptop. You'll just publish it there. Once that happens, the program starts processing the data, and through some magical way you get your output. So first your data gets into the cluster, then your code gets into the cluster. Yeah.
So, why I don't need to give data, or is it, what data am I giving? Because it's all there, right?
No, data you will have to give, right? So for example, in a typical, let's take example of an e-commerce website, okay? Their data gets generated in, part of it is in database and part of it is in a logs, which is in a web server. You want to run some reports on the data. So you need to transport the data first, right? See, one is your business applications that are running. They typically call it as OLTP. All your transactional stuff is running here. So let's take example, we have these two groups. This particular servers are taking care of hardcore business right now. And then these guys are one who will play with the data to get some reports. All the data from here has to go to the cluster for them to run their reports.
So what is there in cluster? Is the data already there in the cluster?
No, see, the data is getting generated by your business every minute. That is getting generated in a separate place. See, how does data warehouse work? Take example, your business is running and it is generating data. In some way you do ETL where you take this data and put it in a data warehouse. Similarly, data is in your OLTP. In some way you will write scripts to put that data inside the Hadoop cluster. It's as good as that. Yeah. Clear?
The cluster by default just has the
Machines.
jobs for handling programs and data.
Yes, programs and data, yes. See, if you forget for a minute for Hadoop, let's say, what does a data warehouse do? I may have my CRM, I may have some sales data, and I may have user history, something. I put everything in a data warehouse to run my reports.
No, I'm using Hadoop because I cannot process, my data is getting generated faster than I can process it, right?
Fantastic, correct.
So, I have to process it.
Yes.
Then why to use Hadoop?
See, your data is getting generated faster than you process it, right? The place where it gets generated and the place where it is get processed are two different rooms. You need to transport the data because the place where it is getting generated, you would not want to put Hadoop on top of it there to slow down your process. See, one is your OLTP, okay, where all your data is getting generated in a minute. To play with that data, you need to take that data and put it somewhere else because a place where it is getting generated, you will not play there only. You are getting the point. You need separate rooms to do that, right? That is the way you go about it.
Master in short is nothing but a computer.
It's a computer. Everything is a computer.
Right, it's a computer. So then when we are transferring the data from the storage location to this place, would it have its limitations of space? Like, the amount of data generated, say, is 100 terabytes, and then
For now, I said just look at it as a magic. It will get clear in the next slides. But the idea is this. This guy, the master, is just the brain, has no data, only the brain. And he's smart guy. These guys are the one which will store the data. Now, as he rightly said, as we started, one machine cannot store more than 64 terabytes of data. But if I have one master and 1000 nodes, I am suddenly able to, basically cater to now 64,000 terabyte. This guy in some magical way will put the data, and then it will run the programs on top of it. Got it? But there's a very interesting point that came in. All the data need not go via this guy. This guy will just give you, this is where you should go and put the data, and the laptop, basically the client, will automatically talk to the data node and put the data. So the master is not a bottleneck. Okay? Clear? You have to push. You have to use utilities which you can run to pull the data from somewhere, but typically some way it has to be pushed inside it. Some way you have to push it. Yes. No. Somebody has to push it. It's a file system. Exactly. Correct. You have to push the data. Yes. Push the data into it. Correct. Correct. You still need to write a program, right? There are utilities which will pull data for you. No, it's purely master driven. The first time you are pushing data, it has to be through master. When you decide to write certain data, first you have to contact the master node, and it will tell you where to put the data in some magical way, which we'll talk about later on. I don't want to bring it right now because that will, basically confuse everyone. But first time when you're writing, you'll have to talk to the master node. You'll always have to go to master node. Correct. Yes, you will have to query that, and then it will get data in some way for you. But the difference is, the name node isn't a a bottleneck. It will give you some meta information, and then you as a client will connect to that data node. So not for every communication, you are just going to get that first information and leave the name node from there on. That's a slight difference.
So it's like a file system. The name node is like a directory entry.
Exactly.
And then the actual data is actually the file sector, so that will be your nodes.
Perfectly put. Okay, fantastic question. HDFS is an unintelligent, dumb data store. It does not do anything with your data. It will just take all the data as it is, and then you write programs to transform them. So day one, when you are pulling data from 10 different sources, the data will still remain the same. It is just a file system. You write programs to make them, the way you want. Clear? All right. I want to play quick, just to make sure that everybody kind of understands the terminology. So we understood how things work. Can I have 6 people here? Any 6? Don't be shy. Wow, good that, yeah, 2 guys, you guys be here. Yeah, you both look like managers, so you guys be here. Yeah, Mukund, just come over. Yeah, 6 guys. Yeah. So you have Mukund standing here, you standing there, and you guys standing. One more guy. Yeah, that's fine. Mukund, if you could be front and you could be front. No, face this way. Face this way. You be here and you two stand behind him. Simple. I think you face this way, yeah. And you have 2 guys and you have 2 guys. That's it, yeah. So visualize Hadoop as 2 teams. Okay? There is a team called storage and there is a team called fantastic. He is the manager of storage team. What's his name? Fantastic. His name is name node. He is the manager for processing. What's his name? Fantastic. Now the process, and at the same time, you have, can you be here? You be here? Yeah. You come over here, and you come over here. Yeah. And you two stand together. Yeah. Behind. Yeah. Now, this is another machine. He is working for Mukund. So he is part of the storage team. What is his name on the slave node? Fantastic. He is data node. And this guy is fantastic. Now data node and task tracker will always be on the same machine. So this is one machine. This is machine number 2. It's a pair. And on the manager side you have name node and job tracker. Now if I want to process tons of data, I first go to him and say, hey, I want storage. You take this file and you store it the way you want. So I give him data and he puts that data on these 2 machines. I'll tell right now how they will work. So he puts the data. After he's written with the data, he gives me acknowledgement data is there with me right now. Then I go to this guy and I give him my jar file and tell him, Mukund has given you some data. Please process and give me the output. So he is the guy who knows where data is, but the data is stored here. He is the guy who gets the program, but processing is done by these 2 guys. Now I'll tell you how exactly this works. Let's say I give 640 MB of data. How much? Typically, that's all the data is broken into chunks of 64 MB. How much? You can customize it, but typically it's 64 MB. So when I'm talking about 640 MB, how many blocks will be made? Fantastic. So when I go to him, he breaks that and gives him 5 blocks and gives him 5 blocks. Okay. After they are done with 5 blocks, then I give him the program. He will keep one jar for him and one same Java program for both of them and ask him to process how many blocks? So basically he will initiate 5 Java programs. Same programs 5 times, provided he has that much RAM. Similarly, that guy will process how many blocks? This is how Hadoop works. The first terminology you need to know is name node, the master, job tracker, data node, task tracker. His job is to process only these 5 blocks. There are 2 more dimensions to it, but that will confuse, but I'll still tell you. If you guys have doubts, just let me know. When he's writing these 10 blocks, he will also replicate the blocks, each block 3 times, just for safety. How many blocks? Each block 3 times. So basically when I am giving him 10 blocks, how many blocks is he writing? 30. But other 20 are not used till the original is damaged. Clear? Along with that, he being a manager and he being a manager, this guy is just programming, that's fine. But he stores all the addresses in his brain. If he goes down, we don't know how blocks are broken. So he is single point of failure. So there is one more machine they normally put called a secondary name node that is copying his brain every now and then. So if he goes down, you take all the logs from that and run it and bring the name node up again. That's how Hadoop will work. So there is replication. By default it is, you can go to 10, it's okay. The amount of money you have, you can replicate it. So basically what I'm trying to say is, if you buy a hardware which will store 100 terabytes, and if your replication factor is 3, you can typically store 25 terabytes, because 25 into 3, 75 terabyte, you will leave some space, typically 25% for the operating system and other things. Making sense? So this is how this whole ecosystem would work. Any questions on this? You don't have to replicate. Processing is just program. It's a Java file. If he goes down, the whole system comes down. There has to be a downtime. Okay. Task tracker. Correct. Huh. Yeah, he will be updated. So, okay. When these all are, okay, so we'll talk about failures also now because they are covered in first slide, but let's say we are playing this, so we'll talk about it. Every 2 seconds or certain seconds, this guy keeps on telling him I am alive. That's called heartbeat. Similarly, every 2 to 3 seconds, this guy keeps on sending him a signal that I am alive. Okay? And this is how the heartbeat mechanism works. So assuming he goes down, he knows that he's gone down and he'll tell the other guy to take care of the whole job. So job will complete, but it will be slower because one person is gone, but it will not stop.
So when one goes down, who is responsible for telling the other person?
Job tracker. All programs go off. It's on the same. So, yeah.
So the replication is not just for name. So name node is more critical. So we have
Name node is critical because what, see, this guy is a processing guy. Basically, he takes a program and runs it. So there is no data in him. What will you back up? This guy really has all the data. So you back up him. A processing guy just takes, if you see, he's a smart guy, but he just takes a Java program and runs it for you. There's no rocket science. But this guy knows how I have broken the blocks and where I have kept it. So that's why you need a backup for name node. Now we will talk about a bit about this. Now this is a question for if you could answer, like if I could have 3 points, I take everyone for coffee if you guys meet me outside. If you see this as Hadoop, how it is better than typical distributed system? I'm covering that later on, but any 3 points you tell, it will be fantastic. We saw what is typical distributed system. We understood how Hadoop works. Any questions on how Hadoop works? Now you tell me how it is better than the previous one that we saw. Why? Okay. Fantastic. So one part is data locality. So in typical distributed system, data was traveling to the program. Here, program is traveling to the, clear? Why? Because data is written only once and now programs are traveling to it. In previous case, what was happening? Every time Java was reading 1 terabyte of data. That's not the case. Program is traveling, data always stays. Clear? Yeah, so somebody said less network traffic. Can someone explain why it is less network traffic? You are right, but how? Not exactly. So I have already answered that, yeah, data is only written once. So we are not transporting every now and then, it stays in a same machine. The data node and the task tracker, they are working in a same machine. So there is no network requirement after the data is written. Right. One more point. That's precisely what we spoke about right now. One more point, yeah. See that 3 copies are made only once, and it gives you another benefit of that I'll talk. Yeah, correct. Okay. In typical distributed system, every time you run a program, every Java program is reading 1 terabyte of data on the network. Here also Java will read, but it is not reading on the network. So you write data only once. After that you transport the programs. That's fine, but you are reading it only once when the program is written. Only once, that's all I'm saying. See, visualize this way. I have a storage area network, this storage area network, that is storing 70 terabytes of data. Every Java program I give, he reads all the data, takes it back with him, processes and writes back. Okay, it's one time, no problem. In a year you write, on the same data you write 55 programs. How many times he's reading that? Comparing to that, you put that data, put it once inside, and the guy locally is operating on top of it. Even if data is correct, even if you do every hour, the problem is this. Here, if you see, you are every time reading the data. Here, you are writing it only once. That's fine. It's only once, but yeah. Everything is replicated thrice. But even if you look at your use case, if you see, here I'll write once, that's fair. Even here you will have some backup mechanism if you know the network team is there. But here you write it once and you run programs on top of it. So you're writing only once, and after that the local guy is taking care of it. If you take off a distributed system, every time you want to read, you're transporting that much data. Making sense? What if you want to write another program on top of this data? You again read 1 terabyte of data from the network.
So now another way to look at it is if you have an update of 10 MB,
Yeah.
you are only replicating 30 MB of data. If you, on the earlier system, if you just update 10 MB and you run your program again, you're again transporting 1 terabyte.
Exactly.
So 1 terabyte is again going to all the programs and all the stuff.
Yes. So the idea is, here your program is traveling to the data. In typical distributed system, the data is traveling to the program. And even in here, you will need some way to write data once. And if there is a system administrator smart enough, he will replicate it at least once more. So you're anyways taking the pain. But here, every time you run a program, you will have to read that data, which is the case here, it's local forever. One more point. Different nodes. It's again once. Yeah, but if you do every replication on the same machine, one machine goes down, it defeats the purpose of replication. Yeah. See, network is required. We are not saying in this you don't need network. The point is, if you calculate in numbers, in this case network bandwidth is much more required once, and it can become a bottleneck. Here that is not going to be the case. So we are not saying, yeah, network bandwidth is required, but here it becomes a bottleneck, there it will not become a bottleneck. And if you go by numbers, the usage will be less in this comparing to this. You can go by numbers and you would automatically figure out. Huh? Why? Why? Fantastic. Yeah. Doesn't that require? No, it will not require synchronous. We'll talk about that. Yeah, we'll talk about that. When we run our first MapReduce program, that will get clear to you. Yeah. So yeah. Brilliant. So if you see, this system already has, you know, all the infrastructure in place for you. You just need to write your program. To elaborate, what happens when something fails? Assuming a data node fails, the job tracker will assign work to some other guy and tell him to operate on the replication of this. So that's also taken care for you. Failures are inbuilt, taken care of you. So for example, let's visualize. He's processing 5 blocks. So basically, totally how many blocks he has? 15 replication wise. And even he has this. Assuming now these two go off because they are down. Can you just go off? Yeah, no. Only these two. Assuming this node fails, what happens? He gets no heartbeat and he figures out that, okay, one node is down. He will instruct that guy that after you are finished with your 5 blocks, you have to run other 5 blocks. As a programmer, it's not your business anymore. And he will then run on the replicated blocks and get you the output. As a programmer, you're not worried about how failures are handled completely. When you write your program, we will see how to write a program and all. You will not write even a single line which will tell, okay, you know what if failure happens, do something. It's just taken care for you. Is this clear so far? Any questions on this? from the task tracker, it's considered to be down. It's considered to be down, and then if they don't receive, so see, if data node is not sending heartbeat, it's considered to be dead. Correct. Yeah, so the idea is this, the payload of heartbeat is 1 byte. I am alive, 1 byte. So transporting that is a separate Java process that, you know, transporting 1 byte is nothing.
I'm saying that if at all one node is taking 10 minutes and let's say there are backup nodes on which I can work on,
Okay.
then is there any mechanism that I can change this? I mean, I can
Okay.
ask the process to get killed on that.
Fantastic. So there is a mechanism, I don't want to get into it, but I'll tell you. So anybody getting confused, ignore it. There is something called speculative execution. Now imagine this scenario. These both are managers. He figures out that that guy is not having a very good configuration. Okay. So he will put same task to that guy also. And whoever finishes first, his output will be taken, other process will be killed. You will have to enable that in your configuration, saying speculative execution enabled. So what happens is, systems with poor configuration, their process will automatically be run somewhere else, and Hadoop will say, I'll run it here also. Whoever wins, I'll take his output and kill the other process. It's called speculative execution. But yeah, it's like way too deep. So anybody who's finding it, you know, just ignore it. Yeah. Any questions with how Hadoop works? So I think this whole, whenever you forget this, this example will, you know, clarify it. I am sure everybody will remember Mukund for that matter. So he's the name node. Yeah.
You said the task and the data in the same machine, right?
Yeah.
He has replicated the same data thrice.
He's replicated thrice. Yeah. Correct.
So both nodes are active working on.
They are active working for their, see, he's having 15 blocks, but you will process only 5 which are original. He will process only his 5. So they are working on their part. They are not working on your data.
Same data is being sent. So if there are three,
Yes. So it will be, see, yeah, same. Yeah.
For the processing programming, it is specific to the specific topic like Java or what is
Yeah, we will talk about that also. You'll have to wait. Probably after the break. Yeah, you guys can move. If everybody is clear, we can let them. You guys can take their photographs to remember, okay, who was who. Yeah. Yeah. Thanks, thanks. Yeah. Proximity is very important, yes. So if it is replicated on 3 blocks, as a client you say, I want to read do.log, the nearest block will be taken and displayed. Hmm. Does everybody get his question? Please listen him carefully. He's brought up a fantastic point. I'll answer that, but if you could just stand up and, yeah, go ahead. Yeah, just pass on. Fantastic question. Go ahead. Hmm. Correct. So part of his question is, while we are replicating, there are two dimensions to his question. While replication is being taken care, will we be able to read the data? Second, typically when we are reading something, the nearest block will come to show the data. Correct? What if some other node has some better update and we are reading something which is old. So there are two dimensions to your questions, right? First, Hadoop is a read-only file system. You can insert data, you cannot update data. So there is no chance of locks, there is no chance of latency issues, anything. Part one. Part two, till the data is completely written, you cannot read it. So fantastic question, but these are 2 points which you really have to remember. First, once a file goes in, you cannot update the file. Part one. Part number two, till the block and the file is complete. Let's say you are writing 1 gigabyte of file. Till that 1 gigabyte of complete monolithic file is not written inside HDFS, you cannot read it, no matter what. Clear? Yes, yes. But the idea is this. If you see, you visualize Hadoop as a data warehouse, where data is coming and you are just playing with it. So you would not want to update that data. So Hadoop is not a real-time system which you will be using like a database. You will be using it for reporting purposes. That's one. When you are updating the data, you will be putting it as a new file instead of recreating the whole data set. So that's how you will go about it. Yeah, we can have it. Any questions before we go for break? Yeah. Of the storage? There is a secondary name node, right, who's backing up everything. Yeah. So the latest version that is released right now solves this problem by calling something called high availability, where you have the master node and a standby node. As soon as the master goes down, the standby takes over. The latest version. But that's a pretty complex concept, and that's why we just don't, to start with, and people have not really gone about deploying them in production because there is very limited documentation around it. So in 3 months you will see that in production, but the latest version is pretty new. So people haven't really migrated to that in production, but that problem is solved. It's called high availability. Correct. Okay. Okay. We can take that in break because people don't know what is edge base. So I don't want to add something new and confuse everyone. So I'll certainly take, if everybody is interested, I'll certainly take one session in coming days for edge base. So, but let's keep that out for now. Yeah. Report. Output. We'll after the break.
So
ब्रेक के बाद
Okay. Yeah.
we'll have a break for 15 minutes. Okay, we have some snacks outside. So let's come back in 15 minutes so that we can continue and complete it on time. Okay, thanks.
So we get started. How was the tea? All right. Couple of things. So first, there's a limit to what can be covered. So now, this is not a marketing pitch or something, just to let you guys know. Next week, there is a 2-day workshop that we are conducting where it will be 8 hours theory and 8 hours practical on Hadoop. It will be with Seed Infotech. So anybody wants to get in touch, feel free to. But it's just for your information, that's it. So I'm not hard selling something. So it's a 2-day workshop which will cover all of Hadoop, which will cover how to write programs, how to set up Hadoop on a single machine, and how to set up Hadoop on a cluster of machines. So that will be next Saturday, Sunday. It will be with Seed Infotech. You guys can have my email address, or you guys can get in touch with Seed Infotech, anybody who's interested. So it's 16 hours training overall. Saturday, Sunday, yeah, complete weekend. All right. Any questions? All right. I just wanted to emphasize a point of what we were discussing about. So there is one more way to, basically look at this whole problem. So if you say you have your disks distributed, okay, when I'm reading from SAN, there is a limit to how much you can read from a disk, which can be like 100 megabits per second. So when all Java programs are reading from the same store, the capacity remains the same. So the max you can get is 100 megabits per second. The best SAN in the world may give you 150 megabits per second. In this scenario, you are having 100 different disks, physically separate disks. So if one disk is giving you 150, there are 1000 disks, you are getting it 150 multiplied by 1000. So that's why this system wins against this where the storage is same. Making sense? Clear? Okay. But yeah, thanks for bringing up. I would probably next time maybe put a slide also in my next sessions where we could basically do all the calculations to see, how it is better. So thanks for bringing up this point. This will help me in my next trainings basically. Yeah, so we get started. So most of what we played in this whole thing is now just part of the slide. So we'll read through, and if you guys have any questions, just So what actually happens? Data is broken into file splits of typically 64 to 128 MB based on your configuration, and the blocks are moved to different nodes. Once all the blocks are moved, the Hadoop framework passes the program to each node. We saw that. Job tracker then starts scheduling programs on individual nodes. So the job tracker talks to the task trackers and schedules the program. Once all the nodes are done, output is written back. We will see how output gets aggregated in a minute. A lot of you had questions on this. So before we really get to the question of how output gets basically aggregated, let's put some more thought on the storage part. So MapReduce has two components. What are they? That's two programs. Hadoop has two components. Yeah, my mistake. Hadoop has two components. HDFS and? Awesome. So let's first talk about the storage part of it. That's storage is good. So for Hadoop to be able to process the files, the file have to be in HDFS. We've already discussed that. HDFS is responsible for storing data on cluster of machines. So HDFS takes care of the storage part, the storage management. Data is normally split into blocks of 64 to 128 MB and spread across the cluster. By default, when you install by default, each block is replicated 3 times. The replication factor can be lowered or increased based on your wish. You can very well have it 1, that is like no replication factor if you are confident that your system will never go down. You can have it 5 if you feel that it will always go down, and also depends on the money you have. To ensure that data is not lost, similar blocks are always replicated on different nodes. It's very logical. A bit more about it. When we say that Hadoop was completely based on the white papers that were built by Google, or they were made by Google. The HDFS, basically the part is basically completely built on something called Google's file system called GFS. So the white paper spoke about how GFS works, and then they just built HDFS on top of it, basically, using the knowledge. Operates on top of a native file system. You have your Linux machine. When you put Hadoop on top of it, so HDFS is working on top of your existing file system. Provides replicated storage of data on a cheap commodity hardware. Is this visible behind, or you want to shut on the light? Okay. Performs best with small number of large files. We'll talk about it. So when we talk about storage, which are the processes that take care of it? Who were they? No, no task tracker. Who told task tracker? Who was taking care of the storage? Data node and name node. Correct. For HDFS to be accessible, name node has to be up all the time. We spoke about that. So name node is a single point of failure. You mitigate that risk with secondary name node. In the latest version, there is something called high availability, where once one name node goes down, the other comes up directly. So it's no more called as a single point of failure also. This is how the name node works. When you first decide to write a file, let's say you have a file which is user, so now you are inside HDFS. The file name is user hadoop data.log. Assuming that this file was 256 MB, so how many blocks will make? If 64 is one block, we'll have 4 blocks. So let's say the block ID is 1, 2, 3, 4. Now this metadata is stored in the name node. So basically Mukund only stores this part. Then these are broken here and replicated 3 times. Making sense? So we are talking about the storage component only. We've not got to the programming part. Clear? This was HDFS. Now let's talk about the processing part. Processing part can be tricky at times to understand, but you know, we'll get there. So MapReduce is the data processing component of Hadoop. It attains the task of data processing by distributing tasks across the nodes. Task to each node, each task on the node processes data that is locally. We saw that example that this guy was only processing data that was with the data node. So typically you would not use data which is on the network, only on the local machine. Consists of 2 phases, map and reduce. Somebody answered it correctly. So in between map and reduce, there is a small phase called sort and shuffle. We'll look at map, reduce, and probably play one more real world exercise. So few volunteers be ready to come over in some time. Now let's quickly look at this. Assume that we have some text file. Let's say it's called data.txt. Okay? And the goal is to count how many words are there in, basically how many times each word has occurred. So take example that we have a file which says, hi, how are you, where have you been, where can I find you, and are you there? Let's say these are the 4 lines. The goal is to find out how many times each word has come. Hi has come 1 time. How has come 1 time. Are twice. You is 4 times. So basically you just want to figure out in a pile of text, how many times each word has occurred. That's my goal. Clear? So we'll see how we break it down, but let's say for now this is my goal. In MapReduce, what you would do is, in default format, the line number is your key. You can customize it, but in default, the line number is your key, and the whole line is your value. So what MapReduce understands is key and value pair, nothing else. It's a slightly different way of visualizing programs, but it can only take data and output data in key and value pair. Okay? So, yeah, so if something is sounding confusing, it will get clear over, you know, once we move. So your line number is key and value is the line number. So the whole value of line. So in this case, key is 1 and value is hi, how are you? Clear? then the action starts. We had two guys who are task trackers, okay? In this case, let's say we have 4 nodes, take example, or one node can run multiple processes, that's fine. But for now, let's say we had 4 nodes. Each guy will take one block of data. So if there are 4 lines, one guy will take, hi, how are you, process it. Another guy will take this, third guy will take this block, and fourth guy will take that block. And he will perform the operation only on the individual data. Making sense? If not, just hold on for some time. So the guy who was processing would only process his blocks. He completes and comes up with his own recommendation that, okay, this is the output that I see. What he gets, he takes every key and value pair. So see this, for each word in value, what is the value? Each word in value, emit word comma 1. That's the count. Just get 1. From here, there is a small sort and shuffle phase, and all the keys, they come together and they look like this. So all the maps, they did their job. Now we have keys identifying everything. All the keys come together. And you get this output. By the way, these keys are sorted by key. They are in this slide, they are not, but they are sorted. So basically, R will be the first guy. So R 1, 1. So all the maps did their job. Now you are consolidating all the keys, and then you go to the reducer. In this case, reducer is 1, there can be multiple reducers. What reducer does, he now aggregates everything. So if you see, he got U 1, 1, 1, 1. So the output will be U, comma. So the reducer is aggregating everything. For each value, for each V in value, so we said key and value, key, and this is an array of values. For each V in value, sum is equal to sum plus V. So first time it will be 1, second time it will be 1 plus 1, 1 plus 1, 1 plus 1. And that's how you get to the output. This is map reduce. How many of you are clear with this? Huh? Key, and this is an array actually, array of values, and you will iterate on top of it to get the values. Is it clear? How many of you are clear? Good number. So there are a good number of people who want some real world example. Let's play a small real world example. So concentrate on the real world example, because I think if you remember that, you mastered the concept. Okay. This is very easy if you really remember that, you know how it really works. Can I have 4 volunteers coming over? Any 4 guys? Not the same guys. Yeah, why everybody so shy? All right, question to audience. How many cards are there in a pack of cards? So many gamblers here, right? Okay, so you stand here. Yeah, stand over here. Now let's say I don't do gambling. I don't know how many cards of each shape are there. How many are there? Let's say I don't know that. So I want to calculate that now. Somehow, you know, never played, so it's okay. You guys can stand in the same line, just together, yeah. So it's a different exercise, no name node and all that stuff, so it's fine. All right. What all shapes are there? Which shapes? Diamond, heart, flower, spade, right? My goal is to, so what is my final output that I'm looking for? Count. Heart 13, spade 13, diamond 13, flower 13. Agree? We all agree to the output? As a programmer, we should know what is my input and what is my output. So we know the output also, right? Now what I do is, I take 52 cards and I give 13 to each. So everybody is a map for me. Clear? I am in my map phase. I take 52 cards, give him any random 13 to this guy, any 13 to this guy, any 13 to this guy, and any 13 to this guy. In the beginning, I have no control who I am giving what. It's just data. So this guy is map 1. He will start processing his 13 cards. So the message to him is, you just focus on your business. Don't worry what other 3 are doing. You don't even know who are others. You just focus. For you, the goal is to just process those 13 cards. Clear? If you look at that program, it is taking that line and it is focusing only on that line. So you focus on 13, you focus on your 13, you focus on 13, and you focus on 13. Clear? Now the map phase, there is a function called map, and that map function is capable of taking only one key value pair at a time. So when I fire this guy, I give him first card. What will he emit as output? Spade, comma. I give him next card. Heart, comma. So he will come up with all his 13 keys, which will be spade, comma 1, heart, comma 1, diamond, comma 1, spade, comma 1 again. He will process everything as single key value, and he will give me his output of 13. Like this, everybody will do their job. Agree? So by the end of map phase, what will the data look like? 52 keys and 52 values. Agree? So far? So this is where our map phase completes. Now there is a sort and shuffle phase. And after sort and shuffle phase, I as a developer decide how many reducers will be there. In this case, I decide there will be only one reducer. So I decide he will be the reducer. So you go back now. So my map phase is over. In my sort and shuffle phase, I will say, bring all the keys together. Just bring all the keys together. So what I'll do is, I'll tell him to give him the data. Give him the data. He has his own data, and he will give his data. And in sort and shuffle phase, all the keys will come together. Clear? So now how the data will look like? Spade, 1, 1, 1, 1. Clear? So this is my sort and shuffle phase. Then the reduce phase starts, where I say, okay, you guys are done. You go back. And this guy will now take every key and add everything that is there. So output will be spade, comma, hearts, comma, diamonds, comma, flowers, comma. Clearer? No, he'll get spade 1, 1. Yeah, right. The reason is, when you talk about map, the function map, he can only see one key value pair at a time. Okay? He's brought a smart point which is advanced, but I'll cover that. But for now, just assume it's only one key and one value. Agree? He will, his program, see, every program will process one block. But in that block, there are multiple key value pairs. So he will take one block, but the map function will take pair at a time. Not clear? Getting confused? Okay, we'll park it for now because I'll explain that. That's the advanced part. But first understand the concept. Let's talk about the nitty-gritty later on. Is the concept clear? How many of you are clear with this example now? Not yet? You're not yet clear? Any questions on the concept perspective? Okay. Shuffling in the sense, now he did his job. He has to give the data. So he's shuffling the data. He is giving his data to him. Because everybody is done with his 13 cards and I say, now you are out. It's okay, now no more to do. So they will give their data to that guy. That's shuffling. Huh? There is a layer, there's a Java program that does for you. You don't have to write that sorting and shuffling logic. Clear? And this is how he comes up with the output. This is map reduce. Now, as he asked the question, I'll tell you. Assuming that there are 4 blocks, 52 cards, we divided into 4 blocks. So how many cards are there in each? When I say that his program, his Java program, is responsible for 13 cards, but the map function can process 1 card at a time. That means The program will run once, and that will loop map function how many times? Clear? Java program, one whole Java program is responsible for 13 cards. The map function is responsible for 1 card at a time. So map will run 13 times. So if there is a block which is 64 MB and it has 20,000 lines, so how many times map will be called? Map function? Making sense? That's how it works. Does that answer your question? It is always unique, yeah. The reason is, that's all I'm saying, precisely that's all I'm saying, that the map function is written in such a way that it will only take one key value pair at a time. It has no visibility that heart has already gone from me. The map function is designed in such a way that it can take only one thing at a time. Yeah. There is an advanced concept. If you see, there is one flaw here. He had 3 hearts. He had 3 hearts, and he had, let's say, 3, 3, 6, 7 hearts. But they all are still sending him 1, 1 only, right? So there is another layer called combiner, which is optional. Combiner will sit with this guy only, and before data goes to reducer, he will, like a mini reducer, reduce the data and give it to him. That's an advanced concept. So if you're not understanding it, just chill out. So that's like a mini reducer. So before he performs operation on whole data, on subset of data, you can perform operation by this guy. Clear? So this is map reduce. Yeah, you guys can. Correct. Okay. So there is agreed limitation that, yeah, you can certainly do everything that you want, but you should be able to break the problem in map and reduce. Take any problem. Yeah. If every output of one execution the output of one will be input to other, then you will have to write multiple map reduce programs to do that. So here is the idea. Take example that, okay, data is depending on each other. Take example of a simple thing. We are not talking about this sorting and all. Let's take a real world example. I have a log file which has users, their city, and their country. Okay. So 192.168.1.1, Sydney, Australia. Okay. I have log of 10 million files, or let's say 10 million records. Now the first thing, let's say, as a programmer, I have to devise, what is my end goal? My end goal is to aggregate everything based on, let's say, the country. Okay, or let's say everything I want to based on the, what do you call, city. Let's say city is my real goal. So what I will do first is, in my first iteration, I will take the data and aggregate everything that is based on the country. I will not take city in the consideration at all. My first MapReduce program will only give me output based on country, with city being a side data. It will be there, but yeah, I'm not going to use it. In my next iteration, I will take that output and break it down. So I may do something like 10 million rows. In my MapReduce, first I put all the blocks. I am processing one key value pair at a time, right? So I will take all the Australias together. So by the end of my first iteration, I may have Australia, comma, city as a key, and the total number. In my next, I may decide to break it down. So the point is, most of the problems that you will face are breakable. It's how you do it. It may sound very limiting to start with, as he felt, but if you smartly do it, it is possible. The benefit of taking this pain is, if you go by a single machine, there's a limit to how much time it takes. But if you are putting the same thing on 1,000 nodes, you can get it done like virtually 1,000 times faster. but you'll have to express programs accordingly. There is a facility to, basically have output of one map reduced to another, to another, to another, to another, n number of chains you can do. Any questions on map reduce? Huh? Correct. Okay. So here is the idea. How do you visualize this data to come in some flat files, right? So there are flat files where people, so let's say your brand is Pepsi. A group of people wrote something about you on Facebook, a group has written on Twitter, and a group has written on something else, okay? Now, all these files, they come either in XML or JSON, whatever you say. Now, first, the program number 1, which I'll write in, let's say, Java would be, break this data into blocks. Everything is a key and value, right? So, first program, what it'll do is, it'll do something like my key is, let's say, Facebook, comma, or let's say good, comma 1, if I'm just doing some sentiment analysis, okay? So, I'll get all the goods, all the bads, and I'll do some data quality operations on top of it. For example, if I know the guy has purchased a service from me, the quality will be 1. See, you are certified buyer. That means you are a genuine guy talking about it, and other than you just, bullshitting around, correct? So there is some function you apply on this data. Then you apply on this data, then you apply on this data. You store intermediate data, then write 4th map reduce program. That will basically take all this data and come up with the output. So that's how you architect it. Because, see, you don't have to look at data as a whole. Everything is a key and value. Whatever is broken into key and value will be brokeable in, map reduce. And it's not domain specific. The idea is that. So, Facebook data, everything is a key and value still. I take one and see what I want to apply on top of it. Take example. I may have a data scientist who wrote a function for me, which is an API, where you pass the sentence and it will tell you whether it is a positive sentiment or a negative sentiment. Let's say some data scientist has written for us, or let's say some third party has written for us. He's exposed the API. In my Java program, in my MapReduce program, I'll first read the line number 1, give it to him. He tells me good or bad. Now my good becomes a key if I only want the count. When do you say something is positive? Let's say 55% people say good, then you are happy. But it's key and value. You finally get the aggregated value. You get from Facebook, you get from Twitter, you get from LinkedIn. Well, the programs have to be different. Why? Because here the structure of data from Facebook will be absolutely different from LinkedIn. There's no solution to it. You will have to basically deal in that in your program. Once you get data from Facebook, Twitter, LinkedIn, then there may be another smart data scientist who says, you give me data from all social media, I may rank social media. So something written on LinkedIn may hold more importance than Facebook. Possible. I mean, that's a data science stuff. And then you finally come up with output saying that in all past 6 months, about Pepsi, people have written 10 million things, out of which 4 million have been good, 4 million have been average, and 2 million have been bad. That's how you come to your sentiment analysis. That's how you will really, go about stuff. Any questions? Yes. Yes. 64 MB. Yeah. Intelligently stores it. Yeah. It's encryptedly stored for you. The idea is this. Yeah. But it's encrypted and stored. So you cannot access that block individually. See. See, you're mixing two things here actually. One is storage, another is processing. If you keep out the processing for now, data is broken into the blocks. That's it. Can be spilled over, possible, but it's broken. Of course it does. It's storage. That's all I'm saying. You keep processing out for a minute. We'll talk about that. That's fine. See, storage manager is a different guy. When you are giving him the blocks, he doesn't care about the processing guy. Agree? Yeah, we'll talk about it. That's fine. He stores as blocks. As a processing part, you tell what is your key and value. You as a programmer are defining my start tag is here and my end tag is here. Take example, you write a program of, let's say, be it XML or be it, let's say, another file where every 4 lines my line changes. So instead of line end, every 4 lines there is a paragraph ending and I want to take that as my key. That you define. Clear? Now, if the key value pair does not find that particular end tag, it will take that whole key and give it to the other job tracker to process that. So there are two different things. Processing, the storage guy doesn't care about how processing will happen. Processing, you define what is your key and value. Okay. So as a programmer, first you have to define what is your start and end tag. In your, while you're processing, okay, as a programmer you will have this clear in your head that this is my separator. So assuming that my start tag and end tag has 10 gigabytes of data. But first you will define what is my start tag and end tag. Okay. When the processing starts, if it is spilling over the blocks, Hadoop internally takes care of that. Basically, one block is not able to do it. But the point is, it is your responsibility as a programmer to define what's your start and end. Take example, 1 GB is a very, ambitious, nobody would want to have 1 GB data in an XML, but let's take a small example of every 4 lines, it will be a value. I don't want to have my key value ending at same line, it will be 4 lines. In one tag? In one tag.
Not in one tag, there will be a couple of tags in there.
Correct. That's all I'm saying. That you need to separate out. See, data can be of any form. I have no arguments with that. What I'm trying to say is, you are defining the separators. Take example, I have 1,000 terabytes of data. In one of my projects, we were processing 32,000 gigabytes of data, of video data, all stored as logs. Now, the separator was line end. Okay. Now, it may be possible that 64 MB, not everything would be ending on the same line. Possible? It might have spilled over, but that's storage. These are two different functions. Storage doesn't care how processing is going to work. Agree? So it just broke. When you write your program, you as a user are defining that every new line ending is my one key value pair. See, that processing part you are defining, not the program. So I say that every line end is my end. But one of the block, it was not having a line end, but it went to another line. Very possible. Then MapReduce takes care of assigning that particular key value to the next guy who has the remaining part. I'll probably at the end of it, I'll show you on the whiteboard that we are talking about gigabytes of data, but let's talk about simple 4 lines. Can we assure that all 64 blocks will always end with an end line? Not possible. Storage guy doesn't care about it. Storage guy says it's for processing to bother. And the processing guy would depend on you to tell how to break. Agree that all the data will be monolithic, but there has to be some structure where you as a programmer will tell this is where the two records get separate. In my company, it may be maybe a new line is a new this thing. In your company, it may be tab character. Or it will automatically take care of it. Hadoop will take care of it, but it's the job tracker that basically takes that data and gives it to the other guy to process that part. But you as a programmer have to tell what is the separator. That remains with you, because Hadoop cannot be smart enough to figure out where are you breaking, what are you breaking on. In my company, it may be new line. In your company, maybe log files. Every log would break on a company name. Take example, we are in Synerzip. Let's say every log entry gets separated by a specific word called Synerzip. So you as a programmer will tell, anytime you encounter Synerzip, it's a new line. Whether it's spillover, it's possible, absolutely possible. MapReduce will take care of taking this broken data to the other guy and get it done for you. But that guy does not care, because that guy, while you're storing data, you say Hadoop file system, put my file which is 10 gigabytes. He doesn't even understand what is a breaker. He understands everything is a block. The programmer will have to tell him this is where it's breaking. Data spillage is there, that MapReduce will take care of it. The processing component will take care of it. Because to a processing component, you are very clear saying, these are my separators. Yeah. So even in this case of word count, if you see, we are clearly mentioning that every new line is my one value. Pure, clear separator, that's how you break the data. A line may break, this part will go to the next line and it will be processed. Clear? Yeah. Any questions on MapReduce? Huh? How storage happens in the sense? Processed. A lot of confusion between storage and processing. When data is given to Mukund, he doesn't understand. It's a plain data, that's it. There is no logic behind it. It's a data which is broken. Processing guy, you tell him what is key, what is value. That's what he's doing, metadata. We spoke about that in this slide. Data.log, 4 blocks, 1, 2, 3, 4, they are stored as blocks. Typically, these files are stored in a protected location in your Linux box, and they start with BLK. File? Yes, that's how, yeah. That's how, yeah. So when you on your command line say, I want to read this file, all the blocks get together and they show you the output. Yeah. Hardware has some faults, okay. Okay. Can you just give an example to explain this? Fault? Okay.
We have some failure scenario in the system, okay, and we have uploaded that failure logs
In Hadoop.
in Hadoop, okay, and after uploading that log in the Hadoop, we process that logs.
Correct.
Okay, we have written some algorithm based on for processing that log. Okay, after process means while processing, I need some analytics on that, why this fault is generated or
Correct.
why it's required. So that requires some other input,
You'll have to import that data also inside.
but that is at some other places.
You'll have
Not
to get them inside.
means how I will put it into Hadoop, because that is in the other storage.
There are
And
APIs, see, the
Yeah.
way you are taking your fault data, putting in HDFS, you have to take other data and put it inside.
Mhm. But I don't know, means it may be some terabyte of data. So for each job processing, I cannot put the 1 terabyte of data, because that may big data, because
So-
I don't know which part of data will require for that job processing.
So see, without having access to data, how will you do it otherwise? Let's say if big data was not there, how would you still do it?
Yeah, that's why I'm asking. We can do some analytics based on Hadoop for this.
People are using it that. See, that's all I'm saying. People are exactly using it for, there is something called as network failure analysis,
Right.
where based on the history of your network failures, the system tries to predict when your next equipment probably can fail.
Right.
What they do is they take the history.
Mm-hmm.
They take the lookup algorithms. Basically, see, this data that you're saying is 1 terabyte is less than that, which is algorithms, to figure out the processing. And then you get that analytics on top of it, that you know what, your router has been failing once in a month. Or your switch, which is located in San Francisco, is failing once in 3 days. That all data is in HDFS, you are processing it to get that analytics out of it. People are using it for that already.
But in my scenario, the system, we have a systems, okay, and we have uploading the reports on the Hadoop, okay, and we have some programs that terms and analysis why this is generated, okay.
Okay,
And
so let's do this. Let's take that offline, I think so, because I think that's
Yeah.
pretty specific. Let's take this offline. Any other questions on this? You can decide the number of reducers, but you cannot decide anything other than that. So where the data is going to be located, where maps will run, you don't have any control. See, the idea is this. I'll tell you the logic behind it. If a lot of control on those things are given, first thing, they don't help your business logic. What happens is it increases the complexity. So what Hadoop has done is, it is taken care of all the complexity in such a way that you just focus on your business logic. Now let's say giving a control of where you will run, where you will place your block, and where you will run your map program doesn't help your business anyway. You're getting the point. So, well, for the facility, they would give it, but it is not helping your project or business anyway. So that's why they've abstracted this. Take example of failure, okay? Now in failure case, or take example of heartbeat. Every time data node is giving the heartbeat. Now somebody may say, you know what, can we customize and name node have the heartbeat mechanism? Well, it's possible, but it's not taking the entire. So the idea is, they've abstracted everything for you so that you focus on the business logic. So even sort and shuffle, let's say, sorting is taken care as an internal process. It's an internal process. Why? Because sorting doesn't really, you know, it's no rocket science. So they've just abstracted it for you and they're just doing it for you. So that's the logic behind it. Yeah. Any more questions on this? Is MapReduce clear? Now, if the time is over, we could stop here and wait for the next session, probably, if you guys, or I don't know, what is the time? If time is already passed.
Yeah, I do think we are running a little late.
Huh?
It's close to 7.
Yeah, so probably we can wait for, probably we can cover the next part in some other training. In fact, in next part of this tech meet, I would probably show some hands-on also. Yeah, that's about it.
Yeah, this is it.
Oh.
Nothing much, just a word of thanks to Ravi, to Mukund. I request Vinayak sir to give him a token from Synergip for sparing his time for us and for this session.
Oh. Okay, thank you, sir. Thank you, sir. Thank you, sir. Thanks to everyone for coming. You guys have my email address. Any questions you guys have, feel free to shoot questions. I may take a day off, but I'll certainly respond to any questions you guys have. Anybody who wants to really take the knowledge of Hadoop on the further level, there are certifications in the market. Cloudera is a big vendor around it. So anybody who wants to, go, it's a very comfortable place to be in for next couple of years. A lot of activity will be happening around that.
So on the next meetup, I guess we are, the next topic is on cyber warfare, I believe. That's the next meetup. So keep checking the meetup page, and I'll sync up with Ravi, and whenever he is free, we'll set up maybe another follow-up session on Hadoop. Okay? Thanks.